Hello there. We're going to move on to a new topic in particles and waves. It's called nuclear reactions. And as before, there are a number of subtopics within this topic. So this is topic number 3. There are actually 7 topics in nuclear reactions. So we're getting near to halfway through the particles and waves section. This nuclear reaction section is going to take a couple of lessons, and I'm going to start off with something that may be familiar to people who are doing chemistry. So here's a title for your jotter. If I write anything down on the whiteboard, as usual, please get it down in your jotter. A bit of a long title, but it just summarizes what I'm going to do in this lesson. Atomic number, mass number, and isotopes in nuclear equations. And you should already have written, because I've rubbed it out, you should already have written the overall topic title, which was nuclear reactions. Can't quite fit that in. Nuclear reactions. Okay, so we're going to look at these different things today. And just a little bit of revision to start with. This is work that we've done before, either at National 5 or previously in the standard model section. So just some revision. And we're looking at what goes on, nuclear reactions, what goes on in the nucleus. We're not really concerned at all with what goes on with orbiting electrons. So just a little bit of revision. The nucleus contains protons and neutrons, and our protons have a positive charge and our neutrons are electrically neutral. So that means they have no charge. A plus with a VE written after it is just shorthand for positive. If you don't like plus VE, then you can just write positive charge instead. Okay, now to make an atom overall neutral, there must be an equal number of negative electrons. So we've got our protons. I'll just draw some protons. I'll color them in blue. They're not really blue, but I'll color them in blue. And I'll draw some neutrons. And they're not even necessarily arranged like this. Okay, so I've got protons, which I'm going to draw as blue circles, and neutrons that I'm going to draw as green circles. And in an electrically neutral atom, there must be the same number of orbiting electrons as protons. So if I've got 4 protons here, I must have somewhere orbiting around the outside, going round and round somehow. I'm not really concerned about the electrons, but I must have 4 negative electrons to balance the 4 protons. Now, the only time that can change is if you lose one of these electrons through the process of ionization. So if I got rid of one, then that's become an ionized atom because it's 1 electron short. It's possible actually to add in another electron. So I've now got 5 electrons and only 4 protons, and that's ionization as well. Ionization is either the gaining or losing of electrons. But I'm not really interested in these electrons because this is a section all about nuclear reactions. Okay, so all matter, that's all stuff that makes up everything. All matter is made up of elements. And you should be familiar with all these words. So we're just reminding you about some of these words. And we mainly talk about elements in chemistry, but this is a bit of physics where we've got to use some words that that the chemists have borrowed from the physicists. Each individual element has a different number of protons. So it's actually the number of protons that you have in a nucleus that defines what an element is. So, for example, hydrogen has got 1 proton, helium has got 2 protons, and so you can go on through the list of all the elements which are found in the periodic table, and each element has a number, and that number actually tells you how many protons there are in the nucleus. So hydrogen has got hydrogen. I said that properly. Hydrogen has got 1 proton. Helium, it's got 2 protons. Lithium has got 3 protons. Boron has got 4 protons, and so on. You can go all the way through the periodic table. And the number of the element in the periodic table, as I've said, tells you how many protons there are. Now, you have a periodic table. Your periodic table is in with the data sheet, and you get quite a lot of information in the sheet. You get the whole periodic table, and you've probably thought, if you've looked at the information in the sheets before, you've probably thought, well, why have I got a periodic table when I'm doing physics? And this is the section where you need the periodic table, because the periodic table tells you about the makeup of the nucleus of the atom. Okay, so the number of protons in the nucleus is called the atomic number. And the atomic number has an abbreviation. It's an interesting abbreviation. It's such a long word for such a short idea. An abbreviation for atomic number is the capital letter Z. Now, I have no idea why chemists thought this up, that you're going to have atomic number which starts with the letter A and it's abbreviated to the letter Z. I don't know why that is. There's probably some obscure reason, and it's a bit back to front. I think you might have thought that atomic number should have the abbreviation Z, but it does get worse before it gets better, as we'll come on to in a minute. So this atomic number, or the Z or proton number, tells you the number of protons in the nucleus, and it also tells you the number of the element in the periodic table. So here's an example. If you were to look up in your periodic table and look for the element sodium, you would find that its number in the periodic table is number 11. So that tells you straight away that in the nucleus of a sodium atom, there are 11 protons. So we've got the atomic number, we've got its abbreviation Z, and we've got the number of protons are all equal to 11. And this is true for any element that you look up in the periodic table. If it's got a certain number, that tells you what this thing called the atomic number is. It tells you what the Z or proton number is, which is obviously also equal to the number of protons. Now, what else is there in the nucleus? Obviously, in the nucleus, we also have neutrons. Okay, now if we know that this atomic number is 11, we have another number that we need to look at called the mass number. And the mass number obscurely has an abbreviation, capital letter A. So this is a little bit confusing. You're just going to have to remember this. Atomic number has the abbreviation Z, but the mass number has the abbreviation A. Now, what does the mass number mean? The mass number tells us the number of nucleons in the nucleus. And what is this new word nucleons? I probably mentioned that before in the standard model section, but the word nucleon means particles, the total number of particles in the nucleus. I can't even say it. I'm not doing very well this morning. The mass number tells us the number of nucleons in the nucleus. So that's the total number of particles. Now, what's in the nucleus? Neutrons and protons. So the mass number tells us how many protons and neutrons added together that exist in the nucleus. Okay, so just to summarize that, I've got atomic number Z is the number of protons, and the mass number A is the number of protons added to the number of neutrons. And the number of protons and the number of neutrons added together makes up something called the number of nucleons. Now, if we've got sodium as an example, sodium, we know that Z, the atomic number for sodium, its number in the periodic table is 11. So that tells us that we have 11 protons. Well, a bit of simple maths will tell you how many neutrons there are if you know what the mass number of sodium is. So the mass number of sodium is 23. Now, what is that? That's the number of protons and the number of neutrons. Now, if we know we've got 11 protons and we've got 23 protons and neutrons together, then you must have 23 take away 11 neutrons. And that means we've got 12 neutrons in the nucleus. Okay, so the number of neutrons is always our mass number A, take away our atomic number Z for any element. Okay, so if we look at sodium, we can actually put all this information about sodium into what's called a bit of notation. And a notation is just a shorthand way of giving some basic information about our element sodium. So sodium has the symbol Na, which I think is Latin for the old word for sodium. Sodium's a modern word. The old word for sodium was natrium. And we're going to say, right, we've got 23 protons and neutrons, and I'm going to put that up there, that information I'm going to write at the top, and I've got 11 protons, and I'm going to write that at the bottom. So this is what's called notation, nuclear notation. And it says how many protons and neutrons, write the number at the top, how many protons, write the number at the bottom. And we can do this for any element we like. So in general, that was just for sodium. In general, if we've got an element X, whatever it is, mystery element X, we can write down that we put A at the top and we put Z at the bottom. And remember, A stands for the mass number. There. And Z at the bottom stands for the atomic number. Goes in there. So we could do this for any element we like that we can get the information for, and we can write down the information in what's called the notation for an element, and then from that notation you can tell exactly what goes on in that element. You can say, right, I've got a nucleus that's got 23 nucleons, it's got 23 bits in it, 11 of which are protons, 12 of which are neutrons, and orbiting the neutral sodium atom there must be 11 electrons, because I've got 11 positive protons and 11 negative electrons to balance that out to make it overall a neutral atom. As I said before, we don't do much really about the electrons, and chemists will know a little bit about how the electrons are arranged. They're arranged in things called shells, but that's really left for the chemists to do. Okay, so this is sodium. It's called sodium 23. Okay, sodium 23. Now I want to move on to the next little bit of my title, which is about isotopes. And I'm just going to keep some of this information here. I'm going to write down that sodium has, you don't need to do this again because you've just got it. That's called sodium 23. Now sodium always has 11 protons, but you can have a type of sodium, what's called an isotope of sodium, which has got perhaps one extra neutron, in which case it would look like this in its notation, and you'd call that sodium 24. And sodium 24 has one extra neutron. It might be possible to have a different type of sodium called sodium 22. And that has one less neutron than the most common type of sodium. So this is the most common type. And probably about 99% of all sodium that exists is this type of sodium called sodium 23, and there's a little bit of this different type of sodium, sodium 24, which has an extra neutron, and there's another type of sodium that's got one less neutron, sodium 22. These are called isotopes. So what is an isotope? An isotope is the same element. They're all sodium. Sodium's defined as having 11 protons, but it's got an extra or less neutron in the nucleus, and they're called isotopes. Now, there are, in fact, some other isotopes of sodium, but they're extremely rare, and they're usually radioactive, and they don't hang around very long. They usually have what are called quite short. You'll have done some stuff about half-life in National 5. So you can actually work out what's going on here if we go back and look at our standard notation. It's quite simple. Okay, Z tells you the number of protons. This sodium always has 11 protons. And if we do A minus Z for each one, we can work out how many neutrons there are. So for sodium 23, A minus Z is equal to, I shouldn't really write that like that, A minus Z for sodium 23 is equal to 23 take away 11, which, as we've already said, is 12. That's the most stable common type. If we do sodium 24, A take away Z is 24 take away 11, which is 13, and there's your extra, your one extra neutron there, 12 neutrons there, 13 neutrons there, and obviously sodium 22, A take away Z is 22 take away 11, which is 11 neutrons. So we can work out for any element and its isotopes, we can work out its nuclear configuration using this notation here. So these are all isotopes. So isotopes are the same element, which means the same number of protons, but with different numbers of neutrons in the middle. Right. I've got lots of pages of notes here, and I'm going through lots of pages of whiteboard stuff, and I hope you're getting all this down. Okay. So adding or taking away neutrons doesn't change the chemical composition. It doesn't change the element that you've got. It only changes, because neutrons are neutral. They don't really affect, in fact, they don't at all affect the chemistry of what goes on. So adding extra neutrons or taking away extra neutrons doesn't change the chemical composition. If you could actually add a proton, let's take our 2311 sodium, and then add a proton, then you'd end up with 12 protons. And then that element that has 12 protons is no longer sodium, and you'd have to look it up. So we add a proton, that increases that by 1. You could have this number being any number you like, 22, 23, 24. There would be different isotopes of whatever this new material is. So that could be anything you like there. So what happens if you add a proton? Then the atomic number goes up to 12, and you have to go to your periodic table and say, oh, what's the element with atomic number 12? And it is, in fact, magnesium, I think. You could also, if it was possible, to take my 2311 sodium and subtract or remove a proton, And again, the number at the top could be anything really. Could be 23, 24, 22, doesn't really matter. Not interested in that. What I am interested just at the moment is looking at what happens if you remove a proton. Then this number 11 here goes down to 10, and that means it's become a different element, and you'd have to go back to the periodic table and look up what is element number 10, and it's in fact neon. So adding neutrons chemically doesn't change the atom at all. Adding or taking away protons does change the element, and you have to go and have a look and see what is the new atomic number and work out what the new element is. And you would be expected to do that, depending if you added extra protons, or removed protons. It's quite easy to get protons out. It's a little bit more difficult to add protons in. And we will come back to what happens when you start taking protons out in a minute. Now, one other word I want to introduce you to, just because it can sometimes crop up in exams. We've got what's in the middle of an atom. It's called the nucleus. Sometimes you might come across this word, which is pronounced nuclide, and that just really means exactly the same. So the word nuclide means the same as nucleus. Okay, it's just one new word, but they both mean the same, just in case that crops up anywhere. And you say, well, Mr. Ford never told me what the word nuclide means. It just means the nucleus as well. Okay, so we've looked at atomic number, we've looked at mass number, we've looked at isotopes. We're now going to go and have a look at alpha, beta, and gamma decay. And what does that do to the nucleus of the atom? Now, again, we've already done this in a broad sense. So this is going to be a little bit of revision with some extra stuff added in. So we started off doing alpha decay at National 5. We then did a little bit extra when we did standard model. And we're going to take that a little bit further in this nuclear reactions section. Okay, so section 1 is alpha decay, and then I'll come on and do, secondly, I'll do beta and then gamma. So alpha decay. So revision tells us that alpha is a particle, and it's made up of 2 protons and 2 neutrons. So if you had to draw one, which you wouldn't have to, but if you had to, we'd have 2 protons and we'd have 2 neutrons. Okay, and where would that alpha particle come from? It would come from a much bigger nucleus, which I'm not going to draw and do all the colouring in. I'll just quickly do a bit of scribbling here with some loads and loads of neutrons as well. And we've got a big, heavy nucleus, and that decays. And what the word decay means is it shoots out an alpha particle. So this big nucleus will change into an alpha particle, which goes whizzing off, okay, like that. Now, because it's made up of 2 protons and 2 neutrons, 2 protons, that's the atomic number. So the number of protons is equal to the atomic number. I didn't draw that very well. So Z is equal to the number 2. And what does Z equal number 2 and the number of protons mean? It tells you its position in the periodic table as well. So if you go to the periodic table, you'll find that element number 2 is in fact helium. So an alpha particle is sometimes described as a helium nucleus. It's not carrying electrons with it. There's no electrons here to make it an atom. It's a helium nucleus. So alpha is the same as a helium nucleus. So how would we write down in our notation what a helium nucleus looks like? Well, first of all, we'd give it its element symbol, helium, and we'd say it's got the Z bit at the bottom. Remember, we've got our element with Z at the bottom and A at the top. The atomic number goes at the bottom, which is the number of protons, and there's 2 of them, 2 protons. And we've also got 2 neutrons. So the mass number is the number of protons added to the number of neutrons is 4. So that's our notation for our alpha particle. So it could be written like that. You might sometimes see it written like this, and that's just exactly the same. Or if you just wrote alpha like that. So we've got 3 ways of describing an alpha particle. It's sort of shorthand way of alpha. There's alpha with what makes it up, 2 protons, 4 nucleons. The 4 nucleons is 2 protons and 2 neutrons. But because it's element number 2, we can also write helium. These 3 things are interchangeable. There you go. Right, so moving on with alpha decay. This is still alpha decay. I'm going to do on the next board. Okay, let's have a look at an element, radium. And you can look it up in the periodic table, and it is element number 88. So our notation for radium would be 88, and the most common form of radium is called radium-226. And there are other isotopes like radium-225 or radium-227. Okay, now this is the most common type of radium, and it undergoes alpha decay. So what does that mean? It means that from the nucleus, it spits out 2 protons and 2 neutrons. So what we can do with this notation is we can make an adjustment to this notation here so that we can see what we're left with once the alpha particle's gone away. So I've got 226, got my radium-226, and it's going to decay into something, which I don't know what it is, some sort of mystery element, but it's going to emit a helium nucleus. And this is called a nuclear equation. And what I want to do is find out what that is, this mystery element here. Well, it's quite simple actually, because what we've got to do is we've got to make sure that the numbers on the top on both sides of the equation balance, and the numbers on the bottom on both sides balance. So what does that mean? Well, that means here that this number at the top, to balance this equation, is going to look like this. So I've got, that's supposed to be 88, 226, 88 radium. I know I've got my alpha particle that is emitted, but what have we got left? What's the other missing mystery element? Well, I've got 4 on the right, I've got 226. So what do I have to put in here to balance this up? And it's quite simple, it's 222. And what have I got to put in the bottom here to balance up 88 here and whatever is over here? Well, if I've got 88 and I've lost 2 bits, I must have 86, whatever 86 is. And then I can go away once again and I can look up what element number 86 is, and I would find out that it is the element radon. This is radium. and this is radon. Two different elements that start with the same letter, but the second letter is not the same. Radium was discovered first, so it gets priority over its abbreviation, Ra. Radon discovered later. You can't use Ra again because you've already used it over there, so it's got to be Rn. So this is called a nuclear equation, and you have to make sure that the numbers on the left-hand side balance the total numbers on the right-hand side there. So that's quite straightforward, I hope. So that's alpha decay. That's alpha decay. And you can do the same for any other element, and you'll get some practice at doing some of these a bit later on and identifying what the new mystery element is and working out what its configuration is, what its notation is. Okay, so that was alpha decay. Let's move on to the next one, which is beta decay. Okay, so the revision for beta decay is that an electron is emitted from the nucleus and the very first time we did this, I always get people saying, but there are no electrons in the nucleus, but we know that that is caused by a neutron decaying into a proton. So I've got a neutron, green blob, somewhere in the nucleus, surrounded by loads of other protons and loads of other neutrons. It decays into a proton, and the electron, the negative electron, is shot out and is emitted as a beta particle. So the proton remains in the nucleus. So the neutron started off in the nucleus. The neutron decays into a proton, which, as we did previously, we know that's got a positive charge. The electron's got a negative charge. So we've got this thing called charge conservation going on, that the positive proton, and there's my neutron, if you like, my positive proton is balanced by my neutral electron, and the two charges cancel out to give me no charge at all. So you know that. That was just a bit of revision that you need for this next section. Okay, so different elements will decay in different manners. Where you looked at radium, and radium often decays by giving out a an alpha particle. An element that doesn't do that and gives out a beta particle is the element phosphorus. So phosphorus decays by beta emission. Now phosphorus, letter P, is number 15 in the periodic table. So its atomic number is 15. And a very common isotope of phosphorus is phosphorus 32. There are other types of phosphorus which might have different numbers of neutrons, which will make them different isotopes, like phosphorus 33 or phosphorus 31. And you can see where this is all going with isotopes. Okay, so I know that phosphorus decays it by beta emission. And so what happens, Well, we're going to get something, and we're going to get a mystery element with a different notation and configuration is going to be formed. Okay, so this number 15, remember the number 15 tells you the number of protons. And what is beta decay? Beta decay is actually a neutron changing into a proton, and that proton stays in the nucleus. So we covered this very briefly before. So it's going to decay. When the neutron changes into a proton, which remains in the nucleus, the number of protons goes up. Okay. But overall, the number of neutrons and protons added together stays the same. The neutrons just changed into a proton. So we're down by one neutron and up by one proton, and that cancels each other out. So we've still got 32 of them with our beta particle, and we're going to have to go off to our periodic table and see what happens when our neutron is changed into a proton. The number of protons has gone up by one, and what is the element with one extra proton? You look that up, and it's that element there. Okay, it's silicon. So we've got the beta bit here. Now, this isn't quite right now because I don't have any information here that balances up these numbers. So although I've put beta there, which is okay, the numbers don't seem to balance up like we had before. So what I'm going to have to do is I'm going to have to make some changes here. I'm going to say, right, what does this number here at the top, what does the mass number of a beta particle have to be so that I've got 32 on the left and 32 on the right? Well, I've got 32 on the right already, so this must be 0. It's 32 there, and 32 and 0 still makes 32. And I'm going to do the same again. I've got a 15 there, and I've got a 16. What's this atomic number going to have to be to balance this up? Well, it's going to have to be minus 1. And then 16 minus 1 is 15, and that balances left and right. So there you go. So the configuration of a beta particle, which we know is an electron. Oh, there you go. It's an electron with charge -1. And an electron has almost no mass compared to a neutron or proton. So we're just going to call its mass number 0. Don't forget, we have got some anti-neutrino stuff going on here. If we go back to our standard model, and we really ought to add in our neutrino. It's actually an anti-neutrino when we get beta emission. So how does that look as in terms of its configuration? And it looks like this. So from the standard model, we know that the anti-neutrino has no charge, and it's, we think, virtually massless. We don't know. That's still another thing in physics we're trying to work out. Does the neutrino actually have any mass at all? But if you look here at the mass number of the neutrino is 0, which implies it hasn't got a mass. And its charge, when we did the standard model, we talked about it being like a baby neutron, which is why it's called a neutrino. And this is an anti-neutrino, and we would get the same if we had, this is beta emission, we would get the same as if we had positron emission as well. Okay, so you could we could do that again with positron emission. But the mass number gets a little bit more awkward. The mass number stays the same, but the atomic number here has gone up by 1. With positron emission, the atomic number goes down by 1. And an atom that does this is carbon 11. Carbon 11, it's number 6 in the periodic table, and it decays into boron plus a positron. Now remember, a positron has got a +1 charge. I could write this here, this beta particle, as an electron, because we know it's an electron. So I'm just going to rub that out there and change that to an electron. And this is going to be a positron. So we've got a negative electron and a positron there. And the positron emission is accompanied with not an anti-neutrino, but just a plain ordinary neutrino. And an ordinary neutrino doesn't have the bar across the top. If you have the bar across the top, it makes it an anti-neutrino. So this is positron emission. And this is our more normal beta emission. And all I did was I changed my beta into an electron, because that's actually what it is. Okay, so that's beta decay. And again, there'll be some more chances of doing some problems on this a bit later on as part of your assignment. So that's alpha decay done. That's beta decay done. So lastly, I've got number 3, which is gamma decay or gamma emission. Doesn't matter which word you use. And once again, bit of revision. What is gamma? Gamma is not a particle. And we talk about gamma rays. And what is, if it's not a particle, what is it? They are, in fact, photons or waves of electromagnetic radiation. And you all know that when we did the electromagnetic spectrum, we've talked about this a number of times, but firstly, you were probably introduced to that in 3rd year. And we've got radio waves right down the bottom here. I'm not going to draw this out, radio. And then you move up through visible light, Roy-Gebiv, ultraviolet, X-rays, and then gamma. And gamma is right at the top end of the electromagnetic spectrum, which means that it's got a very short wavelength, very high frequency, but also carries away a lot of energy. So they are photons of electromagnetic radiation that are high energy. So it's got no mass because waves don't have a mass. It's got no charge because waves don't have a charge. And so if you've got a nucleus that gives out some gamma rays, there's no change to the mass, there's no actual change to the structure. The whole structure of the nucleus stays the same. So what do I mean by the word structure of the nucleus? I mean that before and after, before gamma emission and after gamma emission, there's no change in the number of protons, no change in the number of neutrons. The only thing is we've got rid of some energy, and the nucleus actually settles down into a lower energy state and becomes a little bit more stable. So because there's no change in the number of protons, there's no change in the number of neutrons. The equation, the decay equation, doesn't change at all. So an element that decays mostly by gamma ray emission is cobalt 60. And cobalt is number 27 in the periodic table. So it decays into the same thing. It decays into cobalt 60, same number of protons and neutrons, same number of protons, and just emits some gamma. And there's no numbers here, there's no numbers there. It's got to be 0, 27, 27, that's got to be 0. So there's no numbers here. We don't write any numbers here because they only refer to particles, and it's not a particle, it's a wave. Right, so that's covered everything in my title, so I'm going to stop there, and well, I'm just going to stop there, and that's the end of this first bit of the nuclear reactions topic.